In this video, we're going to build off what we talked about in the previous video in order to draw the mechanisms and predict the products in exercise 1312. Now, they're going to give us one of those functional groups that we discussed in the previous video, either aldehydes, ketones, carboxylic acids, or esters. And they're also going to give us one of the reducing agents we discussed, either sodium borohydride or lithium aluminum hydride. And that's what they're giving us here. One note also, just to appreciate the significance of these types of mechanisms and reactions. In the laboratory, it's easiest to use reagents like sodium borohydride or lithium aluminum hydride, but there are analogous compounds in your body, NADH and FADH2, if you remember if those sound familiar from your biology classes. Those have almost in the same type of mechanism as the sodium borohydride and lithium aluminum hydride. Those are also reducing agents and have a mechanism like this on the molecules in your body. Okay, so this LAH is another way of writing lithium aluminum hydride. The way that we saw how to write it before was LiAlH4. And the structure for lithium aluminum hydride is you have an aluminum bonded to 4 hydrogens. That whole thing acts as a sort of unit. As a unit, that whole thing has a negative charge. And the lithium is there to balance that negative charge. Now, in actual studies, in current research, the lithium seems to be playing a role in the mechanism too, but for our purposes, it's not necessary to go into that. It will suffice to use the mechanism that we explored in the previous video. Because aluminum is a metal, it has a low electronegativity, and compared to it, hydrogen is more electronegative, so it pulls the electrons to itself in the bond and becomes slightly negative. That's true for each of these hydrogens. And the aluminum loses the electron density and becomes slightly positive. So what we achieve by bonding hydrogen to aluminum like this is we turn hydrogen into a nucleophile. So where would that attack? Well, the carbon that's double bonded to the oxygen, this carbon here, that is slightly positive because it's losing electron density to the more electronegative oxygen here. And if these terms, I have to assume that you know them in order to cover this in a reasonable amount of time in the video, but if the terms nucleophile and electrophile don't sound familiar to you, I strongly encourage you to watch the videos for them in the Organic Chemistry 1 playlist. Those are terms that will not go away for the rest of this semester. So this hydrogen is slightly negative. It will act as a nucleophile and attack this carbonyl carbon. Remember, a carbonyl is a carbon double bonded to an oxygen. The carbon that's part of that is called the carbonyl carbon. Now, this carbonyl carbon already has 4 bonds. And so if it's going to form this new bond that this curved arrow is trying to communicate, then it's going to have to break one of the bonds it has. The weakest bond breaks. That's the pi bond. Remember, the first bond you ever form between 2 atoms is always a sigma bond, which is the stronger type of bond because the overlap between the orbitals has no interruption. Every bond after the first bond is a pi bond, which is a weaker type of bond. It's only formed between parallel p orbitals, and the overlap between them is interrupted. So the pi bond will break and the electrons go onto the oxygen. And so what we have after this first step of this mechanism is we have this same structure, but the pi bond will be broken and we'll have a hydrogen bonded down here from the lithium aluminum hydride. I'm going to redraw that bond so it's more even. Okay. Now at this point, this oxygen has a full negative charge. So we're almost done. We've reduced the number of bonds to the oxygen, but we just have to stabilize that oxygen now. And that's what the water is doing in this second step. So the water is going to be the source for a proton. You'll do a proton transfer. Excuse me, remember the oxygen is very electronegative. Electronegativity increases as you go up and to the right on the periodic table. Excuse me. And so the oxygen is really electronegative, pulls electron density to itself. The hydrogens then lose it and become slightly positive. So the oxygen here can act as a sort of base and steal one of these slightly positive hydrogens, and the electrons in that bond can snap back onto the most electronegative place nearby, the oxygen of the water. And so what you end up forming after that step is your alcohol. Oops. Now you also have hydroxide floating around the solution. And that will sort of play a tug of war and try to steal the hydrogen back, which is why I have an equilibrium arrow there. But at any given time, you will have some of the alcohol there, and it'll be in pretty good yield. So overall, this is the mechanism. You'd have this hydrogen nucleophile coming from lithium aluminum hydride attacking the carbonyl carbon, breaking the pi bond, and then you just have a proton transfer from the negative oxygen onto the negative oxygen from a proton source. It's usually water. And so this is our final product. Now, these hydrogens here oftentimes won't be drawn because in skeletal structures they're implied, and so this would be the product for that reaction. Now they're asking for both the mechanism and the product. Remember the mechanism and the product. So the product is here, but the mechanism is everything we wrote down. So this whole thing is really part of the answer here. Okay, let's apply that same type of thinking to this next exercise. Let's see if we can draw the mechanism, predict the product for this ketone. And notice that this is a ketone because you have a carbon double bonded to an oxygen with a carbon on both sides of it. So you have a carbonyl with carbons on both sides. That's a ketone. Now in the first step we have LaH, that's lithium aluminum hydride. So LiAlH4. And the way that that looks, you'll want to be able to draw, is aluminum with 4 bonds to hydrogens. That all acts as one sort of functional unit and together has a negative charge. And the lithium has a full positive charge to balance that out. Now the aluminum has very low electronegativity, so it gives its electrons away and becomes slightly positive. The hydrogens gain the electrons, steal it for themselves because they're more electronegative, so they become slightly negative, and therefore they become nucleophiles. Now where would a nucleophile want to attack on this molecule? The oxygen is very negative, electronegative, so it pulls the electron density to itself, becomes slightly negative, and the carbon that it's bonded to loses the electron density, becomes slightly positive. So these negative hydrogens would be attracted to that carbonyl carbon because opposite charges attract. So this hydrogen here can take its electrons and attack the carbonyl carbon. That carbonyl carbon already has 4 bonds, so if it's going to make a new one, then the weakest one, the pi bond, has to break. Those pi electrons go onto the oxygen, which is the most electronegative place nearby. Okay, so after that nucleophilic attack, we will have this oxygen. It had 2 lone pairs before, now it will have 3, and a full negative charge. And the hydrogen nucleophile that we added. So we've reduced the number of bonds to oxygen from 2 to 1 by using lithium aluminum hydride, a strong reducing agent, but we still have to stabilize the negative charge on the oxygen. So we use water. And the water is really just going to be a proton source, a source of hydrogens. Remember, hydrogen only has 1 proton in its nucleus, so you'll often refer to either hydrogen or protons synonymously. So a hydrogen atom is a proton with an electron going around it. If you take the electron away, so you just have an H+, that's really just a proton. So here, oxygen again, really electronegative, pulls electron density to itself. And so the hydrogens become slightly positive. That makes them attractive to this negative oxygen. And you have a proton transfer. It steals that hydrogen, and the electrons in the bond go onto the oxygen of the water. the most electronegative place nearby. And so what you end up with is your alcohol. And that would be the product. Now, I'm going to erase the hydrogen there just because it's implied in the skeletal structure. And so this would be the final product, but the whole thing would be the answer because they were asking for the mechanism in addition to predicting the product. Okay. Now, here we have sodium borohydride and methanol. The principles for this mechanism are going to be really the same. Notice that you don't have the numbers in front because, as we discussed in the previous video, sodium borohydride is a weak reducing agent, so it doesn't react with the solvent in the way that lithium aluminum hydride would, which is why you have to separate them, right? You have this 1 and 2, that means you're separating them in containers in different steps. And notice also the power of these reducing agents. We can have a double bond here, and this will not react with it. This will only react with the carbonyl. Unlike hydrogen gas, H2 gas, in the presence of platinum, palladium, or nickel, as we discussed in the previous video. So sodium borohydride has a really similar structure to lithium aluminum hydride. You have the metal in the middle, so that's going to be the boron here, with 4 hydrogens. And that whole thing will act as one unit. Altogether, that unit will have a negative charge. And the charge on that is going to be balanced by the positive charge on the sodium. So the sodium will be a sort of counter ion that balances the charge there. Now, boron is a metal, and so it has low electronegativity. It loses its electron density and becomes positive to the hydrogens. The hydrogens gain it and become slightly negative. Now, boron is more electronegative than aluminum, so not as much electron density goes onto these hydrogens. So these are weaker nucleophiles, but they're still nucleophiles. And if we look at the ketone, and notice that this is a ketone, we have a carbonyl, carbon double bonded to oxygen, with a carbon on each side of the carbonyl carbon. So we have a ketone. If we look at the ketone, we'll notice that the carbon is losing electron density to the oxygen. The oxygen is really electronegative. It pulls electron density to itself. Electrons to itself become slightly negative, and the carbon it's bonded to becomes slightly positive. And that makes that carbonyl carbon attractive to these hydrogen nucleophiles. So the electrons in this hydrogen here will come in, swoop in, attack the carbonyl carbon, and the weakest bond, the pi bond, will break, and the electrons will go on to the oxygen there. So after that first step, that nucleophilic attack, we have the hydrogen added in. The oxygen, which had 2 lone pairs, will now have 3 and a full negative charge. So we've reduced the number of bonds to the oxygen from 2 to just 1. But we have to stabilize the oxygen. Now in this case, we're not going to use water because we don't have water anywhere here. What we do have is methanol. That's the smallest alcohol you could possibly have. That's what you would get if you took one of the hydrogens in water and replaced it with a methyl group, so CH3. And the methyl group is being represented by the Me in the name, so that stands for methyl. That's not a specific element. Okay, so this is the Me right there, CH3. Okay, so this is really going to serve as a proton source, just like water did. Oxygen is electronegative, pulls electrons to itself. The hydrogen it's bonded to becomes slightly positive. This carbon is slightly positive too, but the hydrogen is more vulnerable because it's more exposed to the environment outside. And so this negative oxygen swoops in, steals the slightly positive hydrogen. The electrons snap back onto the oxygen, and we do a proton transfer. We transfer a hydrogen, an H+, or a proton, from the methanol to what was our ketone. And then somewhere in the solution we have what's called methoxide, this alkoxide here. And that will try to fight back for the hydrogen, and that's why you have this equilibrium here. So you'll have both of these species existing in the beaker, but most of it will actually be the alcohol. It's getting pushed forward because this reaction is irreversible, and so as more and more of this forms, as you add reactant, it pushes equilibrium toward the products, as we discussed briefly in a previous video, using Le Chatelier's principle. So that would be our final product. Now I'm going to erase the hydrogen because it's implied in that skeletal structure. And so we've made our alcohol. That's the product that we'd predict. And this whole thing would be the mechanism that they were asking for. Okay, let's try D. So again, D is exciting because we see that these reducing agents, here it's lithium aluminum hydride, will react selectively. That's very powerful. That makes us artists. We can be better artists with that. We can use a finer chisel to decide where we want to change a molecule. The reducing agents will only attack this carbonyl. They won't attack the alkene. So if we take that molecule, and here I'll draw lithium aluminum hydride, so we have the aluminum in the center with 4 hydrogens all around it. That's going to act as one group that altogether has a full negative charge, and the lithium will have a full positive charge to balance that out. Aluminum has a low electronegativity because it's a metal, so it gives its electron density away to the hydrogens, which become nucleophiles. So really lithium aluminum lithium aluminum hydride is going to function as a hydrogen nucleophile, a source of hydrogen nucleophiles. Now where would that react with our aldehyde? And notice we do have an aldehyde. We have a carbonyl, carbon double bonded to oxygen, with a hydrogen on one side. Well, the carbonyl carbon is slightly positive because it's double bonded to an oxygen, which is very electronegative. So the oxygen pulls electrons to itself, becomes slightly negative, and leaves the carbon missing those electrons, and therefore slightly positive. So these hydrogen nucleophiles can swoop in. They're going to be attracted to that carbonyl carbon. And when they attack, they're going to break the weakest bond. That's the pi bond here. The electrons will go on to the most electronegative place nearby. That's the oxygen. That oxygen has 2 lone pairs right now. Okay, so that's our first step, nucleophilic attack. After that step, what we'll have is a hydrogen on the bottom here. This pi bond will break and turn into a new lone pair. And having all of those electrons always on the oxygen gives it a full negative charge. And here I'll just center that bond a little there. So that's what we have at this point. We've reduced the number of bonds to the oxygen. So we've reduced this compound. The number of bonds to an electronegative element went from 2 to 1. But this is not quite stable yet. So we have water here as a second step as a proton source. So if we have water, the oxygen here is slightly negative. It steals electron density from the hydrogens, which become slightly positive. And the oxygen here swoops in, steals the hydrogen, does a proton transfer. And the electrons in the bond that were keeping the hydrogen attached to the water, those go to the most electronegative place nearby, the oxygen of the water. And so, after this step, we have our alcohol. Also, somewhere in the solution, we'll have hydroxide with a full negative charge, and so these will exist in equilibrium. This will try to steal that hydrogen back. Sometimes it will succeed, and it'll go back here, but then it'll just turn back into this, so it exists in equilibrium. And I'm going to erase those hydrogens because they're implied in the skeletal structure. So this is the product that you would expect to get from that reduction, and this whole thing would be the mechanism for the reduction. Okay, now this one is a little bit longer this one is really a preview of something that we're going to discuss in a future chapter on carboxylic acids and their derivatives. If you look at the original compound here, you'll notice that what we have is an ester. So we have a double carbonyl, carbon double bonded to oxygen, and then on one side we have an oxygen bonded to another carbon. So that's an ester. And the mechanism for this is a little longer. The mechanism for this is something that probably would not be the focus on an exam for this chapter, but will definitely come up in another chapter. We're also going to do one more exercise to show the selectivity between lithium aluminum hydride and sodium borohydride. So even if you're not interested in this ester, the reduction of an ester with lithium aluminum hydride, you should at least stick around in the video if you want to scrub through. Stick around for this, knowing the selectivity of sodium borohydride is something you would want to be able to do on a test. This would be a very fair and possible exam type question, would be something like this one. So stick around for that. Scrub through if you need to. This one is sort of an adventure. This one we're going to do first. So what we have is an ester, and we have lithium aluminum hydride again. So aluminum with the 4 hydrogens all acting as one unit that together has a negative charge, and lithium is going to have a positive charge that counterbalances that. The aluminum is a metal, so it loses its has very low electronegativity, gives its electron density away to the hydrogens, which becomes slightly negative and therefore nucleophiles. So those are going to be attracted to this carbonyl carbon. The carbonyl carbon is bonded to 2 oxygens through 3 bonds, so it's losing a lot of electron density and becomes very slightly positive. These oxygens are slightly negative. So these hydrogens in lithium aluminum hydride can swoop in and attack the carbonyl carbon, break the pi bond, just like we've seen many times. Now that is going to give us an intermediate, and this is called a tetrahedral intermediate. So let me draw it first and we'll see why. So now there's only 1 bond there. This oxygen now has 3 lone pairs instead of 2, so it has a full negative charge. And we have the hydrogen going down. Okay, if you look at this carbon, the carbon in the middle there, that carbon has 4 bonds and 0 lone pairs. When an atom has 4 bonds and 0 lone pairs, it is tetrahedral. So that's the reason why this is called tetrahedral. And it's also an intermediate because the reaction does not stop here. So it's a tetrahedral intermediate. This negative oxygen is flailing around like a flag in the wind, and it's very reactive. Now remember, we haven't added water yet. We're adding excess lithium aluminum hydride, and this excess here really is just an abbreviation for the word excess. That means we're going to have more than one equivalent of this lithium aluminum hydride. So there's no water in this container yet, and this negative oxygen feels the slight positive charge that's still on that carbon there. And it snaps back down towards it to reform the pi bond. But in doing so, it has to kick something off, and the best leaving group, there are no good leaving groups, but the best leaving group here is this oxygen group. Now, that is a bad leaving group, but you'll notice that the compound already has an oxygen with a full negative charge. So it's not a stretch to create another compound with a full negative charge, because it's only going to be as stable or as unstable as the molecule we originally had. So we'll get rid of that negative charge, we'll form the pi bond here. We're going to break this sigma bond, that will form another lone pair, and that will leave as an alkoxide ion, here ethoxide. And again, you might say, wait a second, isn't that really unstable? It is. Wouldn't it want to snap back on? It does. We have an equilibrium reaction. But this is just as unstable, and so it pushes it off again. And so it exists in an equilibrium. I'm going to redraw this so that it reflects the shape of the molecule a little bit more accurately. Anytime you have a double bond, it's trigonal planar. So we have that. Okay, now this floats around in the solution on its own. Sometimes it attacks and recreates this, but sometimes it doesn't. And that's where things get a little interesting. Remember that we have excess lithium aluminum hydride. So we can take another equivalent of lithium aluminum hydride, and that could sort of beat it to it. It could beat this molecule to the carbonyl carbon. Another one of these hydrogen nucleophiles can swoop in, attack that carbonyl carbon there, break the pi bond, and what you'd have after this second attack from excess lithium aluminum hydride is a new bond to a hydrogen, pi bond breaks, becomes a full negative charge, a lone pair with a full negative charge on the oxygen there. Okay, now this is as reduced as it possibly could be. Notice the original molecule had 3 bonds to an electronegative element, oxygen, and now we only have 1. We've reduced it as much as we possibly could without kicking the oxygen off, and so now we're ready to shake our water in. So we'll pour in some water, shake it up, and what'll happen is we'll do a proton transfer, as we've seen before. So the oxygen here is slightly negative, the hydrogens are slightly positive. This negative oxygen here attacks that hydrogen there, the electrons break, the bond breaks, the electrons go into the oxygen nearby. And so that stabilizes the negative charge on this oxygen. And we have our alcohol. Now I'm going to erase the hydrogens here because they're implied in the skeletal structure, and somewhere in the solution we'll also have a hydroxide floating around and wanting to steal back this hydrogen, but it exists there nonetheless. So this is the alcohol that we would end up with, and this whole thing is the mechanism for this process, the reduction of an ester. And that's something that we're going to explore more in a future chapter. The one advantage to looking at it now is if you ever want to master something, always try doing something a little bit harder. And then the thing you want to master, you'll feel more confident about it. And so that's one reason why I think it was good to walk through this mechanism here. Okay. I think this is the last one for this exercise, but it's a really important one. So let's try to do F. And so if you scrubbed through this, if you scrubbed through that last example, this is where you would want to come back in. Now, we mentioned in the previous video how sodium borohydride is a weak reducing agent and lithium aluminum hydride is a strong reducing agent. And so we saw that sodium borohydride can reduce aldehydes and it can reduce ketones, but notice that sodium borohydride cannot reduce carboxylic acids or esters. Only lithium aluminum hydride can do that because aluminum has a lower electronegativity and so creates larger negative charges on the hydrogens, which therefore are stronger nucleophiles. And they have to be strong nucleophiles in order to beat this equilibrium here with the tetrahedral intermediate. This is a terrible leaving group. You need a strong nucleophile to push that reaction forward. Well, here we have sodium borohydride, and we have 2 possible places where it could attack. We have a ketone, so a carbonyl with carbons on both sides, and we have an ester, a carbonyl with an oxygen bonded to another carbon on the other side. Remember that this Me is a methyl group, so it's really a CH3. So actually, I'm going to redraw that so we can see that a little bit more clearly. So that's the same thing. This methyl group is just a CH3. Well, sodium borohydride is only strong enough to attack the ketone. It will not attack the ester, and that's what you need to remember on a test. So if you were to see on a test, if you were to be given sodium borohydride and you have an ester and a ketone or an aldehyde, the sodium borohydride will only attack the ketone or the aldehyde. It will not attack the ester. So in our structure here, we have the positive sodium balancing the borohydride ion. Boron is a metal, so it loses its electron density, becomes slightly positive. Each of those hydrogens becomes slightly negative, and they can act as a nucleophile. Now, here, this ketone will be slightly positive, the oxygen is slightly negative. Now, it's true that this is also slightly positive, and this is also slightly negative, but you will not react there. This is not a strong enough nucleophile to attack that. And I realized that at this point in the course, this might actually look like a better electrophile. I mean, it's bonded to 2 oxygens. Wouldn't it be more positive? And that's really good reasoning. You'll see later in the course why this is actually a weaker electrophile. And part of it has to do with resonance. I don't want to get too far afield here, but remember that one of the 5 resonance patterns, and resonance is crucial. If you don't remember resonance from Organic Chemistry 1, I can't encourage you enough to watch the videos to master that, because it'll come back again and again. But here, one of the 5 patterns was an allylic lone pair. A lone pair 1 atom away from an atom in a double bond. And that's what we have here. So these electrons are actually able to spread out over all 3 of these atoms, and that neutralizes that charge there. So only a stronger nucleophile would attack this position. Sodium borohydride would not. Instead, it will attack the carbon in the ketone. So this hydrogen nucleophile attacks the carbonyl carbon, pi bond breaks, the electrons go up onto that oxygen. What we end up with after that first step is a hydrogen on that carbon. The pi bond breaks, and the electrons go onto this oxygen here, which now has 3 lone pairs instead of just 2. So it should have had, they weren't drawn in, but it had 2 lone pairs here. Okay, and then I'm going to move this bond over just so it's more symmetrical. So we've reduced that ketone, but what we have to do next is to stabilize this negative charge. So we're going to do that with a proton transfer here from methanol, not water. We don't have any water here, so we're going to use methanol as the proton source, the hydrogen source. So we have this OH, and then the CH3. Remember, that's the Me in the methanol. The oxygen is slightly negative. The hydrogen's bonded to it is slightly positive, and so is the carbon, but the hydrogen is more exposed. It's on the outside of the molecule. The carbon is sort of buried, covered by the hydrogens and the oxygen, so it's harder to reach. And so this oxygen steals that hydrogen, the electrons snap back onto the oxygen. You do a proton transfer. And what you end up with after that step is your alcohol. I'm going to erase the hydrogen here because it's implied in the skeletal structure. And so this would be the correct product that you'd predict from this reaction. And the whole thing would be the mechanism that you would want to include to describe how the reaction happens. So the mechanism is really the same as what we've seen before. The one thing you'd want to remember is that sodium borohydride is a weak reducing agent, and so will only reduce aldehydes or ketones. It will not reduce esters or carboxylic acids. So these same types of reactions with the same mechanism are going to happen in biochemistry if you're taking that next semester. And it's just the hydrogen nucleophile, instead of being sodium borohydride or lithium aluminum hydride, will be NADH or FADH2. But hopefully if you master this mechanism, seeing that in the future will just be like seeing an old friend. You'll already understand how the reaction works.